Okay, so those of you who are already seated, please scan this QR code and do the few Padlet quizzes. Okay, all good with the QR code? I'll give you 5 more seconds. Okay, 5, 4, 3, 2, 1. Okay, I almost feel a bit different like this today. Like, you're watching a show and I'm the only one that's playing a show. I guess they have the lights like this because those lights on the ceiling's not working in this lecture theater. But we'll bear with this. So let's look at the first quiz question. Okay. So a white noise process has weak or essentially zero persistence, whether you think this is true or false. So those of you who just come in, okay, I'll give you 5 seconds to scan the QR code. 5, 4, 3, 2, okay, time's up. So coming back to this first quiz. So remember what actually is a white noise process, okay? A white noise process is essentially one that has a zero mean, a constant variance, and no zero correlation. Okay? So basically, any 2 points that is at different time, their correlation is 0. If there is no correlation, okay, which means except for a perfect correlation with itself, then immediately the ACF plot would just drop to 0 and remain at 0 forever. Okay? In this case, a white noise process essentially has no persistence because it's not influenced by its past at all. Okay? So if you recall what we've done on Monday, remember we plot the ACF plot for white noise, okay? We can see that this bar, which is essentially the correlation with itself at lag 0, and all the other correlation with any lag that is greater than 0 or smaller than 0, regardless of how you look at the h, okay? As long as h is different from 0, immediately there's no autocorrelation. So the persistence is 0. There's no persistence, very, very weak persistence, okay? Any past history has no influence on its future. Remember, persistence is about the rate at which the ACF converges to 0, okay? As the data points become further. There is sound, right? Okay. So if the autocorrelation collapses to 0 immediately at the first lag, then basically the persistence is really weak, 0. So this is a correct statement, okay? A white noise process has weak, essentially 0 persistence. And similarly, an IID white noise also has weak or essentially 0 persistence, because IID white noise, essentially they are independent, which is stronger than no serial correlation, okay? So any time series process with no autocorrelation, with no serial correlation has 0 persistence, because the lag just doesn't influence the future. So this is the first quiz question. And the second one, okay? Here we have a random walk. It's a special case of an AR1 model where the autoregressive coefficient is exactly 1. So basically we're saying that alpha 1 is exactly 1. Is this correct or not? Yeah, this should be a very simple one, basically just a definition question. It's correct, okay? An AR1 model, which is essentially that takes this form. And a random walk is essentially the case where the alpha 1, the slope coefficient on the immediate path, is equal to 1. That is what we discussed on Monday, okay? The random walk is the special case of an AR1 model with alpha 1 being 1. So if you got this one incorrect, make sure you read Monday's slides and also the corresponding lecture notes. So this is a correct statement, okay? So basically a random walk means the past shock has permanent effect on the future, because essentially a random walk process is the cumulative sum of all shocks without any diminishing effect. That is what we derived during the lecture on Monday, okay? This expression here. So this is a correct statement. Now, the next one. A high autoregressive coefficient in an AR1 model indicates a rapid dissipation of shock's influence over time. So basically what it's saying is a high alpha 1 means that the shock's influence diminish rapidly over time. Is this correct? So we have quite a balanced book. Now, what does it mean by the shock's influence diminish rapidly over time? Does it stand for weak persistence or it stands for strong persistence? Do you think that stands for weak persistence? Do you think that stands for strong persistence? It stands for weak persistence, okay? Weak persistence basically means the influence of the past quickly vanishes as time passes. So essentially, a rapid dissipation of shock's influence over time represents weak persistence. Now, in an AR1 model, if we have a large alpha 1, would that imply we have the past influence diminish rapidly over time? No, okay? A high autoregressive coefficient represents strong persistence, okay? The larger the alpha 1, the slower the influence of past shocks diminish. So this is a false statement, okay? A high autoregressive coefficient indicates a slow dissipation of shock's influence over time. It shouldn't be a rapid one, it's a slow one, okay? Because the ACF plots would decay gradually, not rapidly. So this is something we talk about on Monday. So we try to derive the condition on the alpha 1 when we have the AR1 representing a stationary time series, okay? And we found that for the YT to have a constant mean, which is equal to alpha naught divided by 1 minus alpha 1, first of all, alpha 1 has to be different from 1 in order for this ratio to be legit, because the denominator can never be 0. And secondly, in order for YT to have a constant variance, okay, that is equal to sigma square u over 1 minus alpha 1 square, not only we require the denominator to be different from 0, so alpha 1 has to be different from 1 in absolute value, but also the variance has to be non-negative, which means the denominator, 1 minus alpha 1 square, has to be positive, strictly positive, okay, given that it cannot be 0. So together, this implies a stationary process, a stationary AR1, would need to have an alpha 1 that is smaller than 1 in absolute value, okay? So basically, if alpha 1 lies between minus 1 and 1, that will ensure a diminishing influence of shocks over time. The smaller the alpha 1, okay, the closer alpha 1 is to 0, the quickly the past shocks influence diminish. And the larger the alpha 1 is, or put it differently, the closer alpha 1 is approaching 1 in absolute value, the slower the diminishing effect, okay? So the diminishing effect is quicker or larger when alpha 1 is small in magnitude, whereas as alpha 1 approaches 1, the diminishing effect is weaker. So just to quickly wrap up on what we didn't manage to finish on Monday. So basically the ACF for the stationary AR1, the autocorrelation function, depends directly on the alpha 1, the autoregressive coefficient. And the autocorrelation at any lag h is essentially the power function of alpha 1. It's alpha 1 to the power h. So essentially what it means is that as long as alpha 1 is different from 1, we have autocorrelation, okay? So if we have alpha 1 different from 1, the past will influence the future. And also, the ACF decays in a geometric way, okay? Because the ACF is equal to alpha 1 to the power h. It's a geometric function. So the speed of this diminishing effect decreases as alpha 1 approaching 1, whereas it increases as alpha 1 approaching 0. So a high alpha 1 suggests increased or large persistent or strong persistent, or you can call it long memory. And we can also see from the ACF plot here, okay? So for these ACF plot, they basically correspond to different values of alpha 1. The top left corner, we have alpha 1 being 0.25, sorry. So top left corner, we have alpha 1 being 0.25, and we can see that the ACF quickly goes to 0 right after the first lag, okay? The first bar, remember, is always the autocorrelation with itself. The second bar stands for autocorrelation at the first lag. The third bar stands for autocorrelation at the second lag. And we can see that already the third bar barely exceeds the 95% confidence band for statistical significance. Okay, so starting from even the second lag, the autocorrelation is not statistically different from 0. And then on the top right corner, we have the ACF for alpha 1 equal to 0.5. And we can see that, in a sense, the ACF decays in a relatively slower rate compared to when alpha 1 is 0.25. At the bottom, we have the 2 for alpha 1 equal to 0.75, and 1 for alpha 1 being 0.95. And we can see that as alpha 1 increases, the rate at which the ACF converges to 0 just gradually becomes smaller. Okay? So alpha 1, the magnitude of alpha 1 is crucial for determining the degree of persistence in an AR1. So coming back to the quiz question, this is false. Okay? It should be a slow dissipation. Now, the next quiz question is that we have a random walk without drift has a constant expected value over time, whereas a random walk with drift has a time-dependent mean. And this is also what we discussed on Monday. And do you think this is right or wrong? Okay, this is a correct statement. We've derived this during the lecture for the one without the drift. The expected value is basically 0. So it's constant over time. Regardless of any time t, it's always 0. Whereas with a drift, essentially the drift term introduces a deterministic trend. And that makes the expected value of the random walk with drift to be linearly dependent on t. Okay, so the random walk with drift has an expected value that depends on time, which is time dependent. So this is a correct statement. Okay? So this is the second last question. And the very last one, we have that an AR1 model implies that YT is correlated with its immediate lag YT minus 1 and uncorrelated with any future lags. Can this be correct, or is it a correct statement? Okay, this is apparently false, and I'll already sort of give you a hint when we were discussing the ACF plot. I mean, clearly we have an ACF for an AR1, and we can see that if you look at all the ACFs, we do have YT correlated with YT minus 2, and as alpha 1 increases, we also have the YT correlated with YT minus 3, or it could correlate with YT minus 4. It's just that in the AR1 case, the correlation between YT and any lag that is greater than 1 has to be through YT minus 1. Okay? So in a sense, it's an indirect correlation. If we look at the AR1 model, which directly links YT with YT minus 1. Okay? So this is a direct correlation. Now, if we write down the equation for YT minus 1, we'll have YT minus 1 directly correlates with YT minus 2. Then YT and YT minus 2 are essentially correlated through this YT minus 1. Okay? The correlation is indirect. Okay? There's no direct correlation, but there's indirect correlation. Then put it together, they are correlated mathematically. And you also see this when you try to derive the recursive equation for an AR1 in the homework problem set. Okay? So coming back to this, this is a false statement. YT can be correlated with any future lags. Okay? An AR1 model does not rule out the correlation between yt and yt minus h for any h that is greater than 1 in absolute value. So these are the quick quizzes questions to check whether you have fully grasped what we've covered in the last 3 lectures. So before we move on to lecture 4, so just to finish on the last slide. So essentially, we just mentioned that the stationary AR1 has an ACF function that decays rapidly as alpha 1 becomes smaller in magnitude. And the fact that the AR1 is having a constant mean what implies mean reversion. Okay? Imagine if you have a constant mean over time, that would mean the sequence will randomly fluctuate around the mean and it will return or cross its mean value fast enough. So another way to see this is if you recall that we derived the AR1 with a mean that is equal to alpha naught over 1 minus alpha 1. Then essentially it means the intercept term can be written as the product of 1 minus alpha 1 and the long run mean mu. Now, imagine if there is no shock, then essentially the next period's y will always lie between the long run mean and the last period's value, given alpha 1 is strictly less than 1 in absolute value. Okay? So basically, what it means is that so imagine this is, imagine this is the mean value mu. Okay, and this is time, and this is yt. So suppose at t1, our yt lies here. This is our y1. Absence of shock at u2, at t equal to 2. So suppose t equal to 2, the u2 is 0. There's no shock. Then essentially, given the AR1 function, we'll have that y2 being equal to 1 minus alpha 1 times the long run mean mu plus alpha 1 times the y1. And just for example, imagine alpha 1 is a half. So basically, we have y2 being a weighted average of the long run mean and its immediate pass. And for example, suppose mu is 0, okay, and y1 is 1. Then that immediately implies y2 will be equal to 0.5. So the next period, y2 will lie here. Okay, this is t equals to 2. And then imagine if the next period also u3 has no shock, then y3 will be half times the long run mean plus half times the value at t equal to 2, its immediate pass. Again, mu is 0, a half times a half, which is 0.25. Then this is y2, and the next period, y3, it will become even closer to its long run mean. Then essentially what we have for a stationary AR1 is absence of shock. Okay, in future period, eventually the time series will be dragged back to its long run value, the long run mean, which is what you could call the equilibrium value, the value without no shocks, absence of shock. Okay, so essentially, eventually as time passes, it will just lie on the long run mean value, absence of any shock. Then imagine, let's say at t equal to 10, there is a random shock that suddenly hits the time series. Okay, let's suppose at u equal to 10, we have, sorry, at t equals to 10, we have, let's say, ut equals to -1. Then, given that, let's say at y10, y9, we are at the long run value 0, then that would imply y10, which is 1 minus 0.5 times the mu plus 0.5 times y9 plus, given that at u10 we have a shock that is different from 0, so we need to plus the shock. This is 0, but the shock pulls the time series away from its mean. So imagine at u10, it will go to here. Okay, so this is y10. The deviation from its long run value is purely driven by the shock. Then imagine after period 10, there's no shock again. Then the mean reversion will again pull the time series gradually back to the long run mean value. Okay, so the mean reversion is a very typical characteristic of any stationary time series. Okay, given that it has to have a constant mean. So this is the mean reversion nature of a time series process, and we can also sort of link it with the ACF. Okay, so if we have strong persistence, the mean reversion, okay, the rate at which the series go back to its long run value will be slower because it has a high persistence, whereas a weakly persistent time series will tend to revert to its mean faster, as characterized by the alpha 1 in the case of a stationary AR1. Okay? So basically, this is what we sort of left over from Monday. So the value of the alpha 1 not only affects the rate at which the ACF converges to 0, but also it affects the rate at which the stationary process converges to its long run mean. They're related, okay? So this is the alpha 1 in a stationary AR1, and the very last plot is just to give you some visual illustration of what a typical time series look like with a negative alpha 1. This is very rare in economics. Okay, so typically you really barely see any empirical studies with a negative alpha 1 because we can't really model GDP. Okay, imagine if the next period's GDP depends negatively on the last period's GDP. That's almost impossible. And imagine if you model GDP growth, okay? The next period's growth depends negatively on the previous period's growth, which is also unlikely the case, okay? So typically, when we discuss AR models, we'll more or less focus on the case where the autoregressive coefficients are positive, okay? Because this is something more common in practice. So this is what was left over on Monday. Oops, sorry. So we've seen the case when we have an AR1 model where the error term is an IID white noise and that it's independent of all the past, okay? So basically, that sort of implies that conditioning on the past, the U has mean 0. This is something we discussed in semester 1, okay? Basically, if the two random variables are independent, then it doesn't matter whether we condition on the other or not. Okay, so ut and the curly yt minus 1, which captures all the past information of y, they are independent, would just imply conditional mean independence. The conditional expectation of ut given all past history of y is 0. And we also see that one of the key criteria for an AR1 to be stationary is that alpha 1 is less than 1 in absolute value. And also see that when alpha 1 is 1, that corresponds to a non-stationary AR1, which is something we call a random walk. So today, we'll talk about the applications of an AR model. How does it actually apply to practical time series? And also talk a bit about higher order AR models. So remember, we're interested in descriptive time series modeling. And we have not yet talked about linear regression. Okay, the white noise process, the random walk process, or the general AR1 process is just a way to characterize the underlying pattern of the time series descriptively. We have not yet said it's a regression model. But how does it relate to a regression model in the usual sense that we've seen in semester 1? So first of all, given the assumption that our error term follows an IID white noise and that it's independent of all past history, the AR1 model essentially defines the conditional expectation of YT given its own past. Okay? So remember what we just said is UT is independent of all past history of Y. Given that they're independent, the conditional expectation of UT given its own past does not depend on its own past, which is just equal to its own expectation. And this is 0, given that UT is a white noise. Okay? A white noise process has 0 mean. Whereas here follows from UT is being independent of YT minus 1. If you don't recall the relationship between independence, conditional mean independence, and orthogonality, you should really check semester 1 notes. Under the topic 1 folder, I think on the last column, there is a note on the relationship between these 3 conditions. Make sure you check topic 1 teaching material. So given we have that the conditional mean of UT given YT minus 1 is 0, then if we now consider the conditional expectation of YT given its own past, okay? So first of all, we plug in the AR1 model for YT, which is alpha naught alpha 1, YT minus 1 plus UT, YT minus 1. Okay? And then, using the linearity of expectation, essentially, we will have the conditional expectation of alpha naught given the past. We have the conditional expectation of alpha 1 times YT minus 1 given all past, and the conditional expectation of UT given all past. So, first of all, this is 0. We've just established that. Now, alpha naught is just a constant, regardless of we condition on something or not. The expectation of a constant is always itself. This is just alpha naught. Now, for the second expectation, alpha 1 is a constant, deterministic, so we can take it out. Okay? So we can take it outside of the expectation. So we have alpha naught plus alpha 1 times the conditional expectation of YT minus 1 given all past information up to T minus 1. But what actually is inside this curly YT minus 1? We have YT minus 1, YT minus 2, YT minus 3, all the way back to Y naught, all the way back to the infinite past, because it essentially collects all past history up to T minus 1. Okay, this is the curly YT minus 1. Then YT minus 1, the immediate past, conditioning on all past information available up to time T minus 1. which contains itself. You condition something on itself, basically it's known, okay? So conditioning something on itself, it's known. You take it as deterministic, take it outside of the expectation. So the conditional expectation of yt minus 1 given all paths is equal to yt minus 1. And similarly, the conditional expectation of yt minus h for any h that is greater than 0, you're conditioning that on itself. So just equal to itself. So generally, the conditional expectation of yt minus h given all past history up to t minus 1, okay, that is just equal to yt minus h itself for any h that is greater than 0. Because given past information, the past is known. There is nothing random. Okay? Expectation of a deterministic variable is equal to the variable itself. So this is why we have that alpha naught plus alpha 1 times yt minus 1 being equal to the conditional expectation of the current observation yt given all past history. Okay? So which is why we have this conditional expectation. Now, coming back to the slides. Remember from semester 1, the conditional expectation solves a prediction problem. Okay? So remember, our linear regression solves the linear prediction problem. It finds the optimal linear function of x that best predicts y. And the conditional expectation of y given x solves a more general prediction problem. It finds the optimal function of x out of the linear and nonlinear one that best predicts y. Okay, so regression function solves the best linear prediction problem. The conditional expectation solves the best general prediction problem. This is from semester 1 lecture. Okay, if you can't recall this, make sure you go back to the lecture on interpretation of univariate regression. That's in topic 1. So that's something you should refresh your memory on. So essentially, we know that the alpha naught plus alpha 1 yt minus 1 is the best general predictor of yt, okay, using all past history. But this is essentially a linear function. Okay, alpha naught plus alpha 1 yt minus 1 is linear in the yt minus 1. So this conditional expectation must also solve the best linear prediction problem, which is essentially our regression problem. We find our regression model by solving the best linear prediction problem by minimizing the mean square prediction error. Okay, this is something you should be familiar with, that we've been talking about all the time. So essentially, the alpha naught and alpha 1 that sort of characterize an AR1 model basically coincides with the beta naught and beta 1, which we found by solving the best linear prediction problem. So in a sense, the way the AR1 model is constructed makes the conditional expectation exactly the same as the population linear regression function. Okay, remember, the population linear regression function is defined by solving this minimization problem, whereas the conditional expectation is defined by having this AR1 model and imposing the assumption that our error term follows an IID white noise and that it is independent of all paths. Okay? By making this assumption, we make the AR1 model, which is something we use to describe the underlying pattern of the time series, mathematically the same as the population linear model, the population linear regression model, okay? So the main takeaway from this slide, okay, everything here doesn't really matter, but what is the main takeaway is that the OLS regression of YT on YT minus 1 will consistently estimate the alphas in our AR1 model, which is why it makes sense to run OLS regression to fit an AR1 model to time series, because the OLS consistently estimates the parameters, the coefficients in the AR1 model. And remember, the alpha 1, it captures the linear dependence between YT and its immediate past, but not necessarily causal. It doesn't represent the causal effect. So as an illustration, remember, I think it was maybe in lecture 2, we sort of talk about the GDP and the GDP growth rate. So we contrast these two. The GDP is a non-stationary time series which has an upward trend, and the ACF is declining at a very slow rate, whereas the growth rate looks more stationary, sort of fluctuate around a constant mean, and that the ACF is vanishing at a really fast rate. So imagine what would happen if we try to fit an AR1 model to both series. Given the non-stationarity characteristics of the real GDP, we would sort of expect the alpha 1 hat to be quite high, close to 1, given that it has strong persistence and that it has an upward trend, which is suggesting something non-stationary. Whereas for the growth rate, given that it looks more stationary and the ACF diminishes quickly, which is weak persistence, we would expect the alpha 1 hat for the growth rate to be much smaller than the one for the real GDP. So what would happen if we try to fit an AR1? So basically, this semester we'll be estimating the model, the time series model, using the function, the dynamic linear model. Okay, that's something in R which you should have seen or you will see in your practical session. So basically, running this function in R, it tells us that our intercept, which is the alpha hat naught, is equal to roughly 0.043. And we also have that the coefficient on the first leg of GDP. Okay, the 1 stands for first leg, the L stands for lag. And basically, that's the first leg of GDP, which is GDP T minus 1. So the coefficient on that is 0.996, which is indeed near unity. Okay, this is suggesting something that it's close to a random walk behavior. Remember, the random walk is where the alpha 1 is equal to 1. Now, in practice, it's really rare that we will see an alpha hat 1 to be exactly equal to 1, given the sampling variation. Okay, so any alpha hat 1 that is close to 1 would sort of warn us the possibility of having a non-stationary time series. Okay, and we'll also see later that typically if we do have non-stationary time series, while the alpha hat 1 is consistent, typically it's it has a downward bias. In finite sample, it would tend to underestimate the true alpha 1 being 1. So any alpha hat 1 that's very large, even 0.8, something like that, you might be concerned about the possibility of non-stationarity. And we'll talk about how to formally test for non-stationarity in chapter 13. Okay? So if we also compare the fitted value with the actual one, it might look a bit more obvious on your own laptop. Okay, so essentially there are two lines here. One is the actual data that we've seen. It's in the blue line. And the red dashed line, basically, it's the fitted value. Okay, it's the GDPT hat, the one that is predicted using our AR1 model. So what we can see is that the AR1 model seems to fit the actual data quite well. They almost overlap with each other, okay? So which is further confirming that we could sort of depict this upward trend using a random walk model. And another thing that you would typically see, although not quite obvious on this plot, maybe a bit more obvious on the plot for the GDP growth rate, is that the red dashed line, the fitted value, tends to lag 1 period behind the actual value that it's predicting. So they will have the same, you can sort of see that they have the same pattern here, but the fitted value always lag 1 period behind. And this is consistent with the fact that we're using an AR1. We're predicting the current period GDP using its immediate past, okay? So the GDP hat at time 2 is very close to the GDP at time 1, okay? So there will always typically a 1 period lag presented when we plot the actual versus the fitted values of an AR1 model. So this is the GDP data. So talking about something related to hypothesis testing, we can always do hypothesis testing as in the usual sense, okay? So we want to test something related on alpha 1, which is typically what we're interested in time series. And we can test this using a t-test. Now, something you have to be careful here is that for any b that is strictly between -1 and 1, basically that corresponds to something that is a stationary AR1, we can always perform standard hypothesis testing. So basically, you can always use the critical values from the standard normal. So for example, the t-value given here, the 779, that's basically the t-statistic for testing that alpha 1 is equal to 0. And given that this is greater than the 1.96, okay, we know that alpha 1 is statistically different from 0 at a 5% significant level. Alternatively, you can also test for something, for example, B being 0.5, that still lies between the -1 and 1. And given this, okay, you can still use the 1.96, the conventional critical value for 5% in a two-sided test. And again, given that the t-statistic is large, we will reject the null. But what is more important to keep in mind right now is that if we're testing whether alpha 1 is equal to 1, that is pointing towards the test of non-stationarity. While we can still compute our test statistic in the usual way, the test statistic does not follow a standard normal under the null hypothesis, okay? So whenever you're testing whether alpha 1 is equal to 1 in an AR1, you should not use the critical values from a standard normal table, okay? And we'll see how to formally test this in chapter 13. We'll get to learn what actually is the distribution under the null hypothesis in this case, and how can we draw a conclusion from that. So this is about the non-stationary GDP data. So I'm going to stop here because it's already 9:50. For the rest, I think it's perfectly fine that you go through them yourself. Or I might spend maybe like 5 to 10 minutes next Monday to quickly wrap up on the rest. Basically, it's just about estimation. But that's it for today. Thanks for coming. And next week, we have our quiz 1. And you'll get the pre-work on Monday. The quiz opens on Wednesday and closes on Friday. Basically, exactly the same structure as last semester, okay? And have a good weekend.